I'd like to introduce our next speaker, Dr. Jelena Srebric, and she's from Penn State and is going to talk to us about modeling, multi-scale modeling.
Okay, thank you, Annie. So it was really great introduction into my talk from Annie, John, and John. And my name is not John. So, but it starts with J, so we rhymed everything together. Very interesting discussions. Buildings are really a big challenge. So we started from a problem, and then we are introducing tools that we are trying to deploy to solve these problems. And the problem is really huge. I would just scratch a little bit surface of multi-scale modeling. There are other approaches. I'm talking about one type of multi-scale modeling in this particular presentation. And also, we'll discuss some potentials and results. How many of you have, because I've heard there were questions about collaboration between architects and engineers, how many of you have heard something that is called Department of Architectural Engineering? Those two words smashed together? Hands? OK, not bad. Maybe 10 people in the room out of 100. The program exists already for 100 years. So it's not a new discipline, and it suffers from all good things that multidisciplinary programs do suffer. Discussions between generalization, specialization, going too deep, too broad, and all of those beautiful things that buildings are plagued with when we start executing this design process and operation. So this is just a different perspective, slightly more general. The numbers are not here. You have seen them. Buildings are enormous energy consumers. But also they are affecting our environment. And so for now, our population is increasing and also rapidly increasing its presentation in urban settlements. And sustainable technologies in built environment could be an answer. I never say it's the answer. There are many different answers to the question. And we need actually much more creative approaches than what we are doing right now. So that's why I'm here today and hope to engage some of you and motivate some of you to participate in our research area, because we need much more people than what we have. An interesting concept and why this area of research is so complex is really that our outdoor environment is connected to indoor environment, and it's really connected directly to you as a human being. You as a human being in this space feel maybe comfortable, maybe uncomfortable, but you should also know that your health can be affected just by sitting and breathing in the same buildings year after year after year after year. And we can talk about that a little bit later on. But this multi-scale presence or existence of this problem is now becoming obvious, not just because we're talking about it, but also because we are sealing our thumb, our signature in that CO2 emissions. And it's not really that our carbon footprint became obvious from industrialization era. If we read a little bit older research on CO2, we can find that ever since we started doing agriculture, we were producing that CO2 that was visible in atmosphere. So we just right now have an unprecedented scale at which we are affecting the Earth atmospheric processes. And that's good and bad. I personally think it's exciting, because for the first time we realized the power of our systems. We did have this population migration from rural to urban, and if you talk to urban planners, there are many different reasons why we did migrate. And they're not just to group people into conducting manufacturing processes. There are also other systems that are serving human population that is organized like that. So, for example, your food services, your sewage, your energy that you're using are also grouped into this organization called urban settlements. You also have a little bit more other interesting services that are grouped, such as education or health services. So those are other reasons why we group in these kind of settlements. And also there are a little bit more interesting other aspects that are related to our creativity and playfulness, such as art and other type of collaborations that we engage as a human being. So in principle, this trend seems to be relentless, and we will organize ourselves in different type of forms and shapes. Right now, we have something that is a historic overlay of a previous era, but we are really starting to develop much more interesting solutions. So we've heard this discussion about potential for having a human grouping themselves into settlements that look like trees. I personally don't know if that's possible or not possible, but what I would tell somebody, especially young students who are very excited, I would say go and explore it. Why not? Maybe it's possible. Maybe I'm just too old and too settled in my way of thinking. I just don't see the possibility. But you can. If you believe in something, you can do it. And we only just need to invent new materials and new other couple of things, and we are done. And usually, young people really love it. They love the challenge. They don't realize how hard it is. And if you let them run and support them, many of them actually come with unbelievable outcomes. So I've been nothing but astonished and surprised at creativity of our young students and findings that they come up with out of these kind of challenging questions. So whether we are similar to School of Fishes, trees, birds on trees, or maybe an ant colony, it's still to be discovered. And maybe it's a combination of all of these solutions parsed together in some useful form. So we do understand that buildings are extremely important. So this demand in energy is only to remain strong, even if we improve the our energy efficiency significantly. As our population is growing, our needs are going to increase. We had different design paradigms in this building industry, and I'm just covering the past 30, 40 years, roughly. So since the 1970s, there was that first energy crisis when we started really worrying about what to do with the buildings. And then we wondered whether we just recirculate all of the air, and then we wonder about whether you're comfortable. We started seeing that by sealing buildings, making them energy efficient and making them comfortable for you also can result in some health, sometimes adverse health outcomes for you as a part of a population. We had reasonable and important security issues. We are currently talking about sustainable technologies and trying to define what sustainable technologies are. It's a big question that we can also spend another 30 minutes to talk about. But future trends are really in looking into opportunities to explore this more dynamic approach to buildings, looking into weather, looking into predictive modeling, understanding how we affect climate change, and in feedback loop, how our health gets affected with our different solutions. So when we talk about sustainable buildings, these are my two favorite sustainable buildings. Right? We have a ski resort in Dubai and Eden project, which is basically a tropical paradise in southern UK. And they are both using a lot of energy, but I tend to consider them to be sustainable buildings. Not because they are really sustainable, but because in terms of the energy consumption, but sustainability can be also seen as a broader concept of how we are going to preserve our ecosystems so that our biology can thrive. And we might be living in a planet sooner or later that is not that user-friendly to our biology. And discovering how to portably take and efficiently take our ecosystems will be extremely important. So these are sustainable buildings probably in the future. At the present day, what we can do in this business, we can look at you personally indoors. And no bias there. We have a lady on a computer in her office working and having her office environment to be comfortable for her. We have energy simulation softwares at present that can provide you how building goes throughout the day in terms of the energy demand. And there are some issues with the accuracy, better or lower, but we are improving that stuff. You can also use computational fluid dynamics as CFD, our beautiful fluid mechanics developments. And we can actually find the interaction between these two simulation tools, and we can go into more details to know what really goes around you as a person. And we can couple these softwares in a loop And with the different fully dynamic coupled approach, we can find hour by hour what's happening in this space. That's a very powerful knowledge that can be transferred to building designers, and it is transferred. So a lot of these developments are right now used for different type of troubleshooting of problems in our designs. Here is just an example. I'm just giving examples to know or to understand what's possible. We looked at the two different systems, something that was called displacement ventilation, similar to an open window, little breeze coming your way. And you can have a thermostat to control the temperature. You can have occupants. You see engineers look at the occupants as cubes. My colleagues architects always get annoyed by this, but we get some useful data for them. And here is a little animation, what happens throughout the day for center of this room or any other kind of room, that particular room that we had set up. We can do that for this room, no doubts about that. And we can find, here is a temperature distribution. Blue is from 20s or 20 degrees Celsius or 70 Fahrenheit. And your 27 is red, which is close to the ceiling. I was not worried about the temperatures at the ceiling because nobody is yet there in this particular setup. And we can see how the temperature changes throughout the day. And I can decide which system will work better for me in this particular space as a building owner. And we can look also here, there are some standards that approximate how human occupants perceive that space. And we can see that displacement ventilation versus this other displacement, the chill ceiling ventilation, had a different temperature stratification from your ankle to your head. And we can find that this particular limit here at 3 that was set by this standard was exceeded for this combined displacement ventilation and chill ceiling in the afternoon. So I knew that you would be uncomfortable there. I don't need you to complain to me. I can actually predict this in a design phase. And we can also look at what happened with the CO2 levels and VOC levels. These are vertical stratifications for volatile organic compounds and CO2. I picked 8 a.m. and 4 p.m. for circles and triangles, and I can actually really know what these distributions would look like. So, sorry. And you can see that actually in the afternoon, my concentration levels for both CO2 and VOCs were lower. Anybody has an idea why that would be the case? And typical source of VOC or volatile organic compounds would be this lovely carpet that we have here. So that ventilation that is diluting CO2 and diluting those VOCs had resulted in a lower concentration. Anybody has a guess? Actually, it was afternoon, so solar radiation was higher through the windows that did not have shades. So the ventilation rates were higher, and therefore dilution was better. So for me, that was great. But from the energy perspective, that was horrible because I was using much more energy to ventilate that space. And therefore, there is a real interesting optimization process where the air quality requirements and demands are in collision with my energy demands. And everybody is now trying to think, how can we do this optimization without really affecting adversely your biology? So just saving energy is not good enough. These are some historic data collection concepts that we had. You can see instrumentation in offices and some omnidirectional air velocity and temperature probes and some gas analyzers. And then we have this little package instrumentation here. So we need better instrumentation. So any of you working on instrumentation, if you want to create portable, small, wireless instruments that are extremely cheap, I'm thinking $5 to $50, that can measure all of the parameters that I need. Why not be ambitious? $5 is not that much. That we can distribute around the building, we need it. We badly need it. If you want to develop new models, we need them. So we need the measured data. And here is an example how well we can predict in the environment with the current simulation tools. We already defined what are critical simulation parameters in terms of the boundary conditions such as diffuser airflow. You can see at the bottom I spent quite a lot of time on these little guys called diffusers because there was a difficulty in deciding how to accurately simulate those, and because all of the airflow in this room is from those diffusers, and if you don't simulate them properly, You are not going to simulate any other transport process appropriately, not heat, not particles, not concentration. So very important problem that was resolved, and now all of these models are actually part of all of the fancy CFD software packages that you buy, and they have specialized package for CFD. So that's what we have done, that by developing new knowledge and letting the industry adopt and enjoy some of this knowledge and using this knowledge the best way they see. And these lines that you can see here was some floor plan and vertical lines. The line here is simulated data, and dots are measured data for a temperature distribution. Incredible precision, considering how complex this airflow field here. And for those who are having some background in fluid mechanics, these are transitional flows at 10 to power 5 Reynolds numbers. Extremely hard to simulate properly. If you go to some transient changes in such environment like this space, I'm just giving you some feeling. You can predict, here is 24 points of the measured data in that room that I have shown you previously, and vertical axis is temperature. So I was able to correctly predict the temperature within half a degree in that room at very different locations. Also, we distributed different tracer gas and compared the concentration in experiments, which are this pink line versus orange line, which were our simulations. So agreement is really nice. So we can do a lot of stuff for indoor environments. And this technology is now deployed to do cutting-edge research on data center cooling, systems optimization, hospital ventilations, some atria and other interesting architectural solutions for buildings. I have to mention that we have found that beautiful buildings, even though we engineers are not very much married to aesthetics, are actually really important for occupants, because we have found that occupants who find their buildings aesthetically pleasing engage in much better maintenance and operation of the building, so they become more energy efficient as a result of that emotional connection to the building. So this building story, building research story is actually deeply human. So we cannot forget about the human factor, either biology or psychology or behavioral science, when we are trying to engineer our systems. These are just some applications. There are many more. So when we got this really wonderful, Chris Pike will be talking about that, LEED certification process that can tell you how well your building is doing or not doing. And there are many criticisms about the system being not quantitative enough or this or that. I really find it to be great, very educational and very informative. We compared this EPA collected base study here. And you can see those were 100 offices randomly selected all across the United States, and occupants were asked how they felt about certain aspects of their environment. And then we did the same study in a building that was nearby our home institution, and was LEED certified, energy efficient, a really nice ventilation system, and we checked how occupants were doing compared to the average US building. And we have found that occupants felt really good about their building. In principle, if you ask them whether the air was dry, too little air, cold, hot, odor, too much movement, humid, smoke, chemical odors, our building performed in all aspects better than the average US office, except in this concept of being too dry. And if you are ever interested, I can tell you what we have found about that. Our occupants were right that something was wrong, but they were wrong about what was wrong. But look at the diagram here. This is a very interesting diagram. Cumulative density function of symptoms per person. When we, again, the list of items that we were looking at included really health outcomes. So there was a respiratory health, cardiovascular health, and much more detailed questions that I don't need to go into right now. But we have found that the cumulative density function for that particular building versus the building's 100 average buildings were actually the same. So occupants were not really doing better. They were just feeling better in that particular building. It's just one case study. I don't draw any conclusions. We are right now on our mission to do our 100 LEED certified buildings and do the comparison and produce scientific results. This was just a little pilot study to tease out the information, whether it was worthwhile pursuing. So what we are doing right now, we are integrating our knowledge You see, I personally worked on this scale a lot. I know how to deal with energy consumption and your comfort and perceptions in indoor spaces. I have colleagues. This is a very nice project funded by NSF under that EFRI project. My colleague John Zayek has his a really great project as well. So all of those projects are going to make a real contribution in this area. And we have found that we could really, or this is our ambition, use some of the Google tools. And if you guys are interested in talking to us, please do so. And an existing data sensoring network that my colleague Matthew Welch, who now works for Google, created. We have our own simulation tool on solar irradiance. I have a little bit of simulation here that I will show you on computational fluid dynamics, outdoor airflow. We can then send the information to indoor spaces. And here is also very neat part. My colleagues from Public Health, School of Public Health at Harvard are helping us to collect some really more detailed data about you as occupants and your health. And we are still banging our heads against the wall on how to specifically to do this and make some recommendations that can be useful to architects, engineers, policymakers, and other stakeholders in this business on how to design or how to use at least these tools and design different urban settlements. Here is an example of our particular campus, and we did a lot of things with this model. We simulated it, we put it in a wind tunnel, we measured, there are all over the campus, we drag our little sensors networks, and I usually get phone calls from Office of Physical Plant asking me, what are you doing now? We tell them we are doing research, so we just hang some data collection systems off lamp posts. That was the best holder that we could come up with without jeopardizing being rejected to distribute our sensor network. And we have models again that we put, these are just 4 building models of this particular dormitory. We have larger models. We'll look into producing new turbulence models for this kind of simulation so they can be quick. You don't want to be waiting for hours and hours at a time to get some useful information about the airflow. And this, again, for those who are in fluid mechanics, this is an interesting model. We can discuss about it and hours on end, but it's very simple what you can see. And we have found that the model predicted a really nice distribution of contaminants behind the building. This was an experiment collected by other research groups. We use a standard method versus our model, and we can find that the distribution of contaminant concentrations in the wake of this building, and it's a very important problem in this particular field, we have found that our model predicts it very nicely, and we are order of magnitude faster in terms of a simulation time required for this application. So you can see, this is again some anonymous campus, like Google campus. And we at that time did not have a distributed sensor network. We just run the simulation for the sake of running it. And I have found very interesting that in this particular case, at that time, just being desperately out of money for instrumentation, I actually went around and asked human occupants of this campus and asked them, was there any area of a campus where they felt high wind velocities in winter, summer, and so on? And we have found that actually at that time, the model was really correctly predicting the high wind velocities. And I don't need to use the names of the buildings, but they're here and here. And it was a very nice wind channeling that later we used in other student project to propose use of wind turbines in those sections of the campus. So, in principle, from these particular outdoor airflow studies, we have found that different urban densities result in different local temperatures. That's not a brainer. But we are producing correlations that will tell you how correlated your urban density is to the convective heat transfer and basically local temperatures for your incoming wind. There is a very interesting story of Houston these days that cannot get cooled with the Galveston Bay breeze, because the urban density is so high that the breeze cannot really enter the city and cool down the city. So Houston is about to see higher and higher temperatures progressively. We are trying to avoid this in other cities, so we are looking into those correlations. That's the main motivation. So also our cooling equipment, and I was looking what would be the rate I can give you some numbers. I did some back of the envelope calculations, how many degrees your city would get warmer and how much your cooling equipment will become less efficient. Let me not disclose those right now, but in principle, there is a significant effect that is worthwhile doing research in details, and we are doing that right now. And again, different cities in the United States have different urban densities, and we are now looking at different cities, dividing them in something that was developed as a concept by my colleagues from geography in urban terrain zones, and we will be able to tell you, hopefully, 4 years down the road, how different urban terrains affect your maybe local energy bills, your local health, your local different things. This is what all of this kind of multi-scale modeling can provide to you. So in my last 8 seconds, I would say we need everything you can think of. All of the engineers in this building right now can actually start working on this problem. And 100 years from now, we will probably have some interesting solutions. So we need sensoring networks, predictive models, enclosure materials, efficient power distribution, power generation, hybrid cooling equipment to improve our footprint, energy footprint, and air quality in buildings. People can think of other things. How do we organize as a communities? So social, engineering, science, policy, you name it, buildings are there for you to tackle them. And as a conclusion, we are all connected in this unifying team and can make a contribution to this research area. Thank you.
Roman Stalker, MIT. Very interesting presentation. I was a bit surprised and found maybe daunting a couple of things that you mentioned. One of them was a detail on the fluid mechanics when you mentioned that modeling the details of airflow inputs is important to predicting overall properties. That the consequence of that would be that we need to model every single detail in this room in order to get it right. That would be extremely daunting in terms of large buildings. The second point was on when you mentioned ski slopes in Abu Dhabi, and you called those sustainable. Initially, I thought that was a joke, actually.
It's half a joke. A teaser.
Okay, I would say that. So it was a joke.
No, go ahead. Like it wasn't a joke. I'm curious about your question. Yeah.
Well, you proposed a very relative or peculiar definition of sustainable as something that can be used for a particular purpose in the future. For example, as an experiment to design, I guess, landing on different planets or living on different planets, for example. Wouldn't it be the case that if we propose such a definition of sustainable, A, that is dangerous, not only in the public opinion and so on, but B, there might be better ways of coming up with experiments to come up with ways of landing on different planets. We don't maybe need to have a ski slope in Abu Dhabi.
Yeah, I won't go to Mars without a ski resort. No, that's what that was not my proposal. I just like these open-minded, open-ended questions because I do agree deeply with you as an engineer that I would like to have very energy efficient, very premeditated, very organized landings on Mars and settlements. That's my motivation. But I do also understand through my exposure to other fields and other people that some of them would find that gross. And if they have enough resources, they will build, and they probably would, build a ski resort. And it's not my business of judging whether that's right or wrong. That was my position. It's humans. We are playful other than just being practical. That was the only message I had in there. With respect to modeling, I can say you're absolutely right. It would be really a daunting task in terms of not just the simulation, but inputting all of these neat, nice details that you have here. So with respect to diffusers and the details in indoor spaces, we spent, I would estimate, 5 years, different research groups, looking at different things, and we have found what's reasonable to put in and what's unreasonable to put in. And the things can be represented, for example, diffusers with their appropriate momentum and mass flow, and the question is just how do you come up with the data from manufacturer catalogs, and we have found that as well. So a design community can really follow the process. You're welcome.
Hi, Audrey Ellerby from Stanford University. I was really intrigued by your comment about the emotional attachment that humans have to buildings and how that can affect just our care of the building and ultimately sort of the sustainability and energy issues. So it was mentioned earlier that there are behavioral modifications that could help to alleviate some of the energy concerns that we have. I was wondering, has anyone looked at how things like dress codes in certain businesses could affect energy usage? So when I'm at home, I can moderate how much energy I'm using by changing my clothing, right? Sure. And so in some way, I can take responsibility for that. Has anyone looked at how different companies who promote more casual dress codes might have different energy uses than buildings that require formal attire?
That's a phenomenal question. I'm not aware of any study like that, and that's probably why the reason we have this conversation. But I can tell you there is a quantifiable thing to be measured there. Absolutely, yes. Your comfort will be affected with your clothing level.
Yeah, just to add to that, Japan adopted a policy where people could dress down so that they could decrease the air conditioner load in their buildings so as to decrease electrical demand.
That sounds very reasonable. And there is another aspect of that adaptation, and I know they are doing it at different universities actually. Always students are a great population to do experiments with because they're open-minded. Yeah? You can gradually increase the temperature and see when the people start really badly complaining about that particular building, so that you learn something about your population. There are some general thermal comfort diagrams that are developed for some generic population, but you can learn about your population. And I do believe if we do this thing right, you will have a really strong interaction between the human population and the building. Building can become itself a little bit more alive. And there are really strong reasons why that not is the case right now. And again, we can talk for another hour about that.
Yeah, so this is Dinah from Purdue. So I'm very interested in your multi-scale modeling. So in this CFD simulation, you have small scales that coexist with larger scales. Then in the simulation, I would expect certain space discretization is needed. So often in our area, we call it meshing. Then the difference, there could be orders of magnitude difference, yes. For example, even beyond machine precision. So for example, if you are doing double precision computing, at most you can capture 16 digits of difference. Then these scales could be beyond the 16 orders of magnitude difference. Then I'm wondering how you handle that.
We're not handling that in such a direct way. It's impossible. And I believe right now it's unnecessary because we don't understand the processes really well. So what we are trying to do is to see what are the drivers from the smaller scale. So can we classify into, I'm just now telling you some things that we are doing. We have no solution to that question. But we are looking into types of spaces, types of buildings, and looking what is the range for their performance with these more detailed small-scale simulations. And then picking up that information to see what out of all of this chaos really comes as the most important things that are affecting the properties at a larger scale. An example would be so many spaces of this kind, how each of the space really affects this building. So if you have laboratories, it overtakes the rest of your building. So I don't need really to spend too much time on everything else. If I can understand your laboratories, I can tell you how to improve energy efficiency of your building. And same thing for a larger scale on your campus. You can find actually on a campus, we are now classifying buildings based on their energy consumption. And we classify them based on whether the building responds to your weather data or does not respond to your weather data at all, and everything in between. And we are finding why is that happening. So those are just examples how we are looking for drivers from a smaller scale that create emerging property on your larger scale. And that's all we can do for now.
Okay, so it's not like co-simulating these scales together?
No, not yet.
I see. Okay, thanks.
Whitney Clella, Pacific Northwest National Labs. Maybe you've already looked at this, but I'd be really curious to combine your models with models of distributed generators to look at the net effect on air pollution emissions inside buildings, because there could be a net decrease in fuel consumption or a net decrease in carbon dioxide emissions, but maybe there's a net increase in air pollution emissions inside the buildings.
Please come forward. I just don't want to monopolize the time. I would just say what we are trying to do on that www.buildingscience.psu.edu, we're trying to actually post as much of the code, as much of the information that we have as we are producing it. And enabling different collaborations, or you working just independently of us, that would be really wonderful. My biggest problem right now is the interface, because if we just dump things, we will cause more problem than good. And if you are understanding the code, we can give you the code, no problems. But there is this Google kind of question that you guys know better than us how to interface with the public, so that we can, or public in terms of the research community, to speed up the development. But there are many interesting questions here.
Tim Dennison from Medtronic. I was just curious, you were talking about the distributed sensor system, and I was wondering, instead of trying to put in that infrastructure, like take advantage of me carrying this around, is there work going on where like I could put in 200 pounds, my preferences for temperature and humidity, and how tolerant of an individual I am, and then so 100 people stream into this room, you get an estimate of the watts that we're going to put out, and then kind of take what's the ideal set point for this room. Is there any advantage that's being taken with mobile devices today?
I actually, we are going to collect data from your mobile devices. Again, these are, because we came to the frontiers, we are trying to figure out what to do. We can really collect the data, and we are right now collecting them from your personal computers, because it's a college campus, so everybody has a computer. Everybody has also PDI device, but we still did not do that part. Yes, we can collect and should collect the data, but the next question is, how do I use it? And if 100 of you provide me a feedback, do I use an average number? Do I group you in the cold people and warm people? Actually, if I have 30 seconds more, I don't know if we are at the end. How many of you feel in this space? I will ask you 3 questions. Cold, neutral, and hot. Usually the scale is longer. There are 5 things. So if you're on the coldish side, to really cold, neutral, to really hot. So make up your mind. You see, now we are starting to discuss this. Okay, so how many of you would feel cold in this space? Okay, we have roughly 30%. How many of you feel neutral? Okay, this is 50%. I'm just counting roughly. And how many of you feel too warm? Roughly 20%. So we had 20% of too hot, 50% neutral, which is great actually, and 30% on the coldish side. That really usually surprises people. If you are in one of these categories, you don't even realize that there are people around you feeling completely different from you. And it's a very interesting controls problem. Again, that I don't do that, but my colleague who is part of the project is doing that. How do we really decide on what to do with this space?
Yeah, then I can ask to borrow your sweater.
Now this is in the area of a creative solution.
Hi, Kathy Bates from Eastman Kodak. Very interesting talk. You spent a lot of time talking about temperature and air quality, which are very important to me in my office. Another thing that's important to me is light quality. Yeah. And I can see a situation where that could also be in tension with the energy consumption of a building. And so I was wondering if you or any of your colleagues have looked at that, if you've done any experiments on students with that. Sure. It might be a little more difficult to do that, but I'd be curious on that.
I mean, I can a little bit advertise work by my collaborator, or there are other people in this particular project. You see this section, this little square to it represents an entire research group that are looking at the, first of all, your solar input on the enclosure, the shading. My colleague's name is Christopher Reinhardt. Shading building to building. So urban density not only affects the wind, but also what in terms of the solar input your building is getting. So 2 of us are talking to each other in our different languages of softwares to see how do we make a better decision that is not just based on wind, but also on solar or solar and wind. And yes, then internally you have a smaller scale process on visual comfort, and he just finished a survey on adaptive visual comfort. I know that he developed a new concept, so yes, visual comfort is part of it. And that particular building that I gave an example had a very low lighting levels because everything was dimmed to save energy. And that was one thing that they modified after our study immediately, was they increased the lighting level because the response was just overwhelming. Nobody wanted to be in that dark building.
Sid Suryanarayan, Colorado State University. Since you talked about multi-scale modeling, and then you're talking about energy management, I would like to hear your opinion about how you computationally handle the different time constants in this modeling. The electrical system has a very short time constant, thermal has long time constants.
So anybody who worked on a cooling of data centers can really appreciate the difference in how our mechanical systems, in terms of, I'm just thinking about, we calculated time constants for that problem at some. So you are talking about seconds, and sometimes I think in milliseconds in your computational efforts, and we are talking about minutes and hours. There is no resolution because the mechanical equipment is thermally inert. So what we can do is we can a little bit predict how your building will be occupied and try to jumpstart mechanical systems. And the reason why those systems are slow, again, the way we do the generation of cooling capacity and rejection, the whole process is roughly 100, 150 years old. We are right now starting to see some innovations, but what you are using in standard buildings is a pretty inert, very old system. We changed the refrigerants a little bit and some aspects of the cooling system, or heating systems, but it's pretty old technology. We don't have a better ways of generating cooling and heating capacity yet, or faster ways. You can use electricity, for example, for heating, but that's outrageously expensive. Yes, go. Oh, computationally. Again, we did the little trick on the emerging properties. So my colleagues provided for the data cooling center, they provided for me the typical loads. And then we started working from the typical loads. So from emerging property of your system loads to our larger scale simulations. That's all we can do. Of course, the question is not yet resolved at those scales. Absolutely. It's a phenomenal research question. And again, I brought this more as a question rather than me having all of the answers. I can share my experiences.
Well, thank you very much.